Hello everyone, my name is Adam Jones. I'm a first year Cash 2 PhD student. The company I'm doing the research for is TATA Steel Packaging, which is based in Llanelli in South Wales. And my research project is the inline coating thickness measurement of packaging electrolytic chromium coated steel. So what I'm going to cover today in this presentation is a little introduction to the partner company, TATA Steel Packaging, a little introduction to the ECCS product, electrolytic chromium coated steel. I'm going to go into describing the problem status the companies are having and where this lies with my research. Then I'm going to talk about the benefits that this research can bring to the company. I'm going to talk a little about the first phase of the project and what I'm doing now and what I plan to do next. And there's also 5 minutes at the end for questions from yourself. So a little introduction to TATA Steel Packaging. So what this company does is produces coated steels for the packaging industry, and typical packaging applications are food and drinks cans, aerosol packaging, bakeware where you cook your food in, and even can ends which you open. And these typical coated products can either be coated with a tin, chromium, which is tin free, on polymer. And what's important for this presentation to do with the polymer is that the electrolytic chromium coated steel acts as a substrate for this polymer coating. And the polymer coating for TATA Steel Packaging is under the brand name of Product. So TATA Steel Packaging have got manufacturing plants based in IJmuiden, Holland, Llanelli in South Wales, which is TROSTRE, and even Duffel in Belgium. So on the left you can see the typical product that's forwarded to the next customer. Typically TATA Steel Packaging would send this product for further processing. And then, like I said earlier, you've got your food and drinks cans and then your lids, etc. So a little introduction to electrolytic chromium coated steel. I'm going to call it ECCS from now on. What, in simple terms, what it consists of is electroplating a chromium onto a steel substrate. And this is done via electrical current through a series of chromate acid solution tanks. And the steel substrate is typically around 0.5 millimeter thick, and the chromium coating is typically around up to a maximum of 20 nanometers thick, so very small. And what this chromium coating is carried out to is firstly a cheaper alternative to the tin plated products, which TATA Steel Packaging also provides. And it's important because this helps prevent again rusting from oxidization, prevents corrosive attack from the contents, which could be salty in nature. It acts as an adhesive for further processing, such as a sticker on these Heinz bean tins. And it also provides a highly decorative finish, so for the end customer, us, it looks cleaner and it looks more appetizing. The reason I've put the Heinz tins on this slide is because Heinz is actually a big customer of TATA Steel Packaging. So as we're going through this presentation, if you could just keep that product in mind, it'll be something good to relate to. So the problem that TATA Steel Packaging in South Wales is facing is in relation to these chromium coatings. So on their production line, they've got an X-ray backscatter system, which was installed in the 1970s. And what this does is measure the center line of the product only to measure this chromium coating. Like I said previously, these chromium coatings are a maximum of 20 nanometers thickness, so very small. And the issue they're having there is when they're doing periodic offline testing every 12 hours with other coated thickness measurement methods, the inline results are not compliant with the offline results. So it's a big problem. And when I went down there to do an investigation as well, I did also notice that the system is only measuring the center line of the product only. So I think a measurement system for the full product width would be very beneficial for them. And because the current system is installed at the end of the production line instead of straight after the process, it renders inline control implementation very difficult. So to compensate for this problem of ensuring this coating measurement weights, They use an excessive plating current, which is an increase in electricity. They're limiting the speed that the production line is run, so they're getting less product output. They're wasting electrolyte to ensure they're overcoating, so there's no pinholes formatted within the product. And what they've tried doing over the years is calibration efforts, which results in cost in research over the years, which has had no to very little significant results. So this problem then leads into my research question, which is to research and develop a novel, so a new, non-destructive and non-contact inline chromium coating measurement system, so it can measure these 20 nanometer thick coatings on this production line that can move 350 meters per minute or 6 meters a second on the full product width, which is 1.2 meters wide. So a few of these requirements that come up in the initial meetings were discussed, and what this system has to be is non-contact, non-destructive. It has to be able to measure with high speed because the product's moving so fast on the production line. It has to be able to measure these nanometer scale coatings, measure the full product width, and measure the top and bottom surface coatings. So a video I got on the left here was taken a few months ago at TROSTRE, and it's just to show you how fast the coated product is moving through the mill. And this is at 200 meters per minute, which was lowered to ensure that there's no pinholes formatted in the product. So the potential benefits that this project will bring, it's going to bring some inline redundancy to the current system and hopefully add some implementation of inline control, so we can compensate real time these chromium coatings to the desired specification. They'll be able to measure over the full product width, where at the moment they're only measuring the center line. You should get greater yield because you can move the production line faster with a good measurement system, and then you're also saving costs in electricity and the chromate acid solution, which I discussed earlier on. And what's good about this research is it can also apply to other industries where you need to measure nanometer scale coatings, which could be the optical coating industries, steel coatings where you use another coating such as zinc, semiconductor industries, so it could be silicon dioxide on a silicon substrate, or it could also be automotive industries when you want to measure the thickness of paint. So the first phase of this project was taken logically. So we found out what the need was, and I've discussed that with you, and the requirements that we needed for this research. And what these requirements did was direct me for a certain amount of objectives which I want to achieve within the first year, which was identifying suitable techniques that can measure these nanoscale coatings with the requirements I've discussed in the previous slides. So what I had to do was, when I went out then and then I did a literature survey and a literature review on similar applications, so to measure nanometer scale coatings, or even potential novel ideas which are currently measured at micron level. And then what I had to do then is conduct an option selection process based on these requirements. So the results I got from this was 3 potential methods, which are all optical in nature, which are reflectometry. You are looking at what the intensity is of reflection from the sample. Ellipsometry, you're going to be looking at what the polarization changes are after reflection from the sample. And interferometry, taking a look at any interference that you get in upon reflection from the sample. So on the left here we've got a typical reflectometer system. So you have a light source, I'll have some reflections at each of the layer interfaces, and then you'll have a detector. The second picture is the samples I've got ready with the sample results for calibration for the new system, and then the third picture is modelling and measurement, and then how you're going to get output. So what I'm doing currently at the moment is simulations into these optical methods. I've obtained the samples and analysis results ready for the practical research phase, and I've also been designing and procuring components for next year. So next year I'm hoping to get on the practical research, further collaboration with a partner company, and the laboratory scale demonstrator for TATA Steel Packaging. Then in the third year, assess feasibility, system upscale, last minute panic, and thesis write-up. Thanks for listening. If you have any feedback, I'd be greatly appreciated. Any questions? Thank you.